What if the most profound discovery in human history is hiding right in front of us, masked as a simple flicker in the dark? We aren't just listening for radio signals anymore, we are hunting for the massive, jagged shadows of alien engineering, passing silently in front of distant stars. By decoding these strange light curves, scientists are trying to finally distinguish between ordinary cosmic dust and the unmistakable silhouette of a Dyson swarm. For decades, the search for life beyond Earth meant one thing: pointing a radio dish at the sky and waiting for a message. Then came a second approach: chemistry. Telescopes like JWST began sniffing the atmospheres of distant worlds, looking for oxygen, methane, or other gases that, together, might hint at biology. It felt like the gold standard. But by 2026, that approach was showing its limits. Here's the problem. Oxygen can be made by living things, sure, but it can also be made by volcanoes, by geology, by chemical reactions that have nothing to do with life at all. Researchers kept running into false positives, faint atmospheric signals from rocky exoplanets that looked tantalizing, until a closer look revealed ordinary planetary chemistry underneath. A world could look alive on paper for years, before scientists realized it was simply venting gas from its crust. Frustrating? Absolutely. And it forced a hard question inside the astronomy community: what if we're searching for the wrong kind of evidence entirely? Because here's the thing about microbes. Even if we found the perfect chemical fingerprint of life on some rocky world 40 light-years away, we still wouldn't know if anyone was home, whether there was a mind behind it, a civilization, a species capable of building something. So a growing number of scientists shifted their focus. Instead of chasing invisible bacteria, they started searching for something almost absurdly bigger, undeniable, physical evidence of planetary-scale engineering. Not a whisper of chemistry, but the shadow of a machine. This is where the story gets strange, and genuinely exciting. The tool researchers reached for wasn't new. It's called the transit method, or occultation, and it's the same basic trick that's found thousands of ordinary exoplanets over the past 2 decades. Here's how it works. When a planet passes in front of its star, from our point of view here on Earth, it blocks a tiny fraction of that star's light. Astronomers measure this as a dip in brightness, a small, temporary dimming that repeats every time the planet completes an orbit. Kepler used this method to find over 2,000 confirmed worlds. TESS is still using it today. But a natural planet leaves a very particular kind of shadow. It's round. It's smooth. The light curve it produces, that graph of brightness dropping and then climbing back up, is symmetrical, almost like a shallow U-shape, because a sphere blocks light evenly as it slides across the star's disk. Now here's the twist. What if the object doing the blocking isn't a sphere at all? Back in 2015, astronomer Tabitha Boyajian and a team of citizen scientists working through NASA's Planet Hunters project stumbled onto something Kepler had never seen before. A star, catalogued as KIC 846-2852, was dimming by as much as 22%, compared to the roughly 1% dip you'd expect from a Jupiter-sized planet. And the dimming wasn't smooth or periodic. It was jagged. Irregular. It looked less like a planet, and more like debris. Or, as some researchers openly speculated at the time, a partial swarm of megastructures. The internet, understandably, lost its mind. Tabby's star, as it came to be known, became the most talked about star in modern astronomy. Was this finally it? The signature of an advanced civilization harvesting the energy of its own sun? Here's where good science does what good science is supposed to do. Researchers didn't just get excited, they got skeptical. Over the following years, teams using NASA's Spitzer and Swift telescopes, along with ground-based observatories, studied exactly how the star dimmed across different wavelengths of light. And they found something telling. The star dimmed more in blue light than in red light. Any solid object, a planet, a swarm of solar panels, a Dyson sphere, would block all colors of light equally as it passed by. Dust doesn't. Dust scatters blue light more than red. The smoking gun, it turned out, pointed toward a natural culprit, an uneven cloud of fine dust particles, less than a micrometer across, orbiting the star. So Tabby's star wasn't an alien megastructure. But here's why that failure actually mattered enormously. It gave astronomers a real, working checklist for telling artificial shadows apart from natural ones. And that checklist is exactly what's driving the current search. Think of it like shadow puppetry, on a cosmic scale. A smooth, spherical planet casts a smooth, predictable shadow. But a swarm of solar collectors, thousands or millions of independent structures orbiting a star at different distances, would cast something completely different, a jagged, asymmetrical dimming pattern that doesn't repeat cleanly, because the shape blocking the light isn't one object, it's a shifting cloud of many. This idea traces back much further than Kepler, actually, all the way to 1960, when physicist Freeman Dyson proposed that a sufficiently advanced civilization, faced with rising energy demands, might eventually build structures to capture a much larger share of their star's total output. Dyson didn't imagine a solid shell, despite how the concept is often drawn in movies and video games. He described something closer to a loose swarm, independent objects on independent orbits, working together to harvest starlight. A Dyson swarm, not a Dyson sphere. And that distinction actually matters for detection. A solid shell would block light from a star almost completely and predictably. A swarm behaves very differently. Individual satellites, or clusters of them, would drift in and out of our line of sight, creating a kind of flicker, a noisy, high-frequency pattern in the data, rather than one clean dip. Distinguishing that flicker from ordinary noise, or from natural clutter like comet fragments and asteroid belts, is exactly the kind of pattern recognition problem that modern machine learning models are now being trained to handle. Feed an algorithm enough light curves, teach it what natural orbital debris looks like, comets breaking apart, asteroid belts settling into stable rings, and what's left over becomes a shortlist worth a much closer look. Dyson himself pointed out something else, something that turned out to be just as important as the shadow itself. Energy doesn't just vanish. Any structure capturing a star's light for power would inevitably re-radiate some of that energy as heat, specifically, as thermal infrared radiation. So a real megastructure wouldn't just leave a footprint in visible light, it should also glow, faintly, in infrared. This gave astronomers a second, independent test. If you find an object with a strange transit pattern and it also shows an unexplained infrared excess, waste heat with no obvious natural source, that's a much stronger case than either signal alone. This waste heat approach isn't hypothetical, either. It's already been tried. The first searches go back to the 1980s, using data from the Infrared Astronomical Satellite, or IRAS. In 2009, Fermilab astronomer Richard Kerrigan revisited that old data and flagged 16 infrared sources worth a second look, while cautioning that most were probably natural. Later, using NASA's WISE All-Sky survey, researchers scanned literally millions of stars for unexplained infrared glow. And the search has only gotten more sophisticated since. In 2024, a team led by Matthias Suazo at Uppsala University combed through data on roughly 5 million stars and identified around 60 candidates showing infrared excesses consistent, in principle, with what a Dyson sphere or swarm might produce. Now, before anyone gets too excited, it's worth being honest about what that actually means. An infrared excess isn't proof of anything artificial. Plenty of natural explanations exist: hot debris disks around young stars, background galaxies that happen to line up behind the star from our point of view, or dust shed by evolved, dying stars. That last one is a genuine headache for this field, because old red giants naturally produce dust that mimics the exact thermal signature scientists are hunting for. In fact, that's precisely what tripped up earlier surveys. Nearly all of the earlier candidates from decades past turned out, on closer inspection, to simply be distant red giants doing what red giants do. Which brings us back to the real challenge at the heart of this entire field, isolating true artificiality from cosmic dust that's just really good at faking it. The Tabby star story is the textbook case here, but it's not the only one. Every serious candidate now has to survive the same gauntlet. Does the dimming pattern repeat with mechanical regularity, or does it wander like natural debris would? Does the light dim evenly across colors, the way a solid object should, or does it scatter blue light more than red, the telltale fingerprint of dust? And does the object carry a thermal infrared signature that can't be explained by an aging star or a coincidental background galaxy? Only when a candidate survives all three tests, geometry, color, and heat, does it earn the label, worthy of further analysis, which, frankly, is the most exciting phrase in this entire field. It doesn't mean, we found aliens. It means, we haven't been able to rule them out yet. And in this line of work, that's often as thrilling as a confirmation. So where does this leave us? Astronomers researching what's sometimes called Dysonian SETI, named after Dyson himself, aren't claiming to have found anyone. What they're building, patiently, survey after survey, is something closer to a filter. A way of sorting through millions of stars, ruling out the boring explanations one by one, and keeping a short, ever-changing list of objects that still don't quite make sense. There's a bigger idea sitting underneath all of this, too. Back in the 1960s, astronomer Nikolai Kardashev proposed a way to rank civilizations, not by their technology or their culture, but by one simple measure, how much energy they're able to harness. A civilization that uses all the energy available on its home planet. One that captures the entire output of its star. And, theoretically, one that taps the energy of an entire galaxy. It's a scale built almost entirely on physics, on power output, which is exactly why a Dyson swarm search fits so naturally into it. If a civilization out there really is climbing that ladder, a star-spanning collector wouldn't just be plausible, it might be one of the most detectable things they could ever build, visible not because they're trying to signal us, but simply because thermodynamics leaves a trace. That's really the quiet appeal of this whole approach. It doesn't require aliens to want to be found. It doesn't depend on a deliberate broadcast, aimed our way, arriving at exactly the right moment. A megastructure, if it exists, would leave evidence behind almost by accident, the same way a lit city leaves a glow visible from space, whether or not anyone down there is thinking about who might be looking up. Where does the search go from here? Facilities already in operation, TESS, JWST, and ground-based survey telescopes, continue gathering exactly the kind of high-cadence photometric data this hunt depends on. Missions being developed for the coming years, built around even more sensitive infrared instruments and longer observation baselines, promise sharper eyes for exactly this kind of anomaly hunting. Wide-field surveys designed primarily to hunt for ordinary exoplanets, the kind capable of scanning huge swaths of the sky for years at a stretch, are, almost as a side effect, generating exactly the long, uninterrupted light curves that a Dyson swarm search depends on. And that's really the quiet advantage this field has right now. Nobody needs to build a telescope specifically to hunt for megastructures. The data is already being collected, for entirely different reasons, sitting in public archives, waiting for someone to ask the right question of it. Every additional year of data means a longer baseline to check for dimming trends, a wider net for catching irregular transits, and better statistics for telling a genuine oddity from a fluke in the noise. And crucially, none of this requires a single new discovery to be exciting. Each survey that comes back empty still narrows the map. It rules out another slice of natural explanations, sharpens the checklist for the next candidate, and quietly raises the bar for what unexplained actually means. And realistically, most of the strange signals turned up along the way will resolve into something explainable, a red giant shedding dust, an unusual debris disk, a background galaxy caught in an unlucky alignment. That's not a disappointing outcome, it's how this kind of science actually works. Ruling things out is how you eventually recognize the one thing that refuses to be ruled out. Here's the honest, almost humbling part of all this. We used to think finding another civilization meant catching a deliberate signal, a message sent our way, arriving at precisely the right moment, aimed at precisely the right star. Now, some of the most careful researchers in this field think we might not need a signal at all, we might just need to know how to read a shadow. A civilization advanced enough to build a Dyson swarm wouldn't need to say a word. The simple laws of thermodynamics would do the talking for them, one flicker of starlight, and one glow of waste heat, at a time. We must hunt for flickering starlight to distinguish between natural debris and genuine transit anomalies. By analyzing light curves for irregular, non-spherical patterns, astronomers are learning to isolate the distinct silhouettes that a Dyson swarm might leave behind. The search has moved beyond chemical signatures alone, using the occultation method to look for massive shadows cast across the cosmos, shadows that, so far, have always turned out to have a natural explanation, but that, someday, might not. So the next time you look up at a clear night sky, remember this. Somewhere in that scatter of stars, sitting quietly in old telescope data, there could be a shadow nobody has fully explained yet. Not a message. Not a broadcast. Just a flicker, waiting for someone patient enough, and skeptical enough, to read it correctly.